Hello and welcome back to the channel, guys. We are doing Leetcode 1261, which is also the problem of the day for today, and it's a tree based question. So without any further ado, let's have a look at what the question statement says. It says given a binary tree with the following rule. So it's the root value should be 0 for any node which is there in the tree. If it is on the left, then its value should be 2 into x plus 1, right? Given that the root has a value of x, and we are going to see that in the test cases. For example, like this. So if the root has the value 0, then the rightwards index should be 2x plus 2, and the leftward should be 2x plus 1. And then same goes for over here as well. Leftward is 2x plus 1, and then the rightwards it's 2x plus 2. So 2 into 1 plus 2, right? Something like that. Now what they're saying is that the binary tree for some reason has become contaminated and all the tree node values have changed to -1. What we have to do is we have to design a find elements class, and then we have to somehow recover the contaminated tree to what it was initially, given that the root was 0. So that's something which is which makes things pretty clear for us how we have to settle all the other non-root values. Initializes the object with a contaminated binary tree and recovers it, and then boolean find it returns true if the target value exists in the recovered binary tree. Alright, sure. So that's basically how the input and output looks like. So if we actually think about it, then you see the very first thing which they're telling me to do is find elements. So they have given me a certain tree, and then they want me to recover it first of all, right? So as soon as they say find elements, I have to recover it. And then I have the values 0 and 2. Now after find elements, I have two calls of the, you can say, find API, and they're asking me to find one which is not there, and then two which is there, so I return false and true respectively, right? Similarly over here, the first thing is going to be find elements, and then they're sort of asking me to search for these three numbers, 1 3 and 5. 1 and 3 are there, 5 is not there. Similarly over here, I first have to recover the tree, then I have to find all these values, 2 3 4 and 5. 2 3 is not present, 4 is not present, 5 is. So that's how it goes. I want to know the maximum number of calls which are going to be um, made to the find function, but I guess that's something which is pretty easy to figure out if I just store all of these numbers in a set, and then I just look up in O of 1 time, right? So tree node dot value is -1, height of binary tree is less than equal to 20, total number of nodes is this, total calls of find. Alright, that's the maximum number of calls is going to be 1000, and then the target is less than 10 to the power 6. What exactly is the target? What exactly is the target? Let's see. Um, so yeah, acha, all right. The number that they want me to find when via the find API, right? So let's try to think about it, how we can come up with an approach in order to solve this problem. So whenever we actually see trees, the first thing which comes to our mind is recursion, obviously, right? Because how otherwise you how what other method do you have in order to traverse a tree? And basically, if we just talk about the most simplest things which we can do with a tree, traverse and search, something like that, the first thing which comes to mind is recursion. If you're not obviously thinking about BFS, but chalo, let's try to think of something. So I have this tree, right? Let me just copy and paste it. I have 5 ones in this sort of a manner over here. Now, how, if I think about how can I recover it, I know for a fact that this value is going to be 0. Okay, I'll probably make a recursive call and see if there is something on its left. If there is, then I'll change its value to 2. Since I'm talking about the left, then I'll change its value to 2x plus 1. And then I'll again call to the left. We're talking about a recursive logic over here, right? So I'll again make the recursive call to the left, and now the previous value for me was this 2x plus 1. So now the value which this node possesses is 2y plus 1. I think. So y is basically this whole value. So the x for this is actually this whole value, right? I'm really trying to say is something which is very simple. 2x plus 1 is 1, and then 2 into 1 plus 1 is 3. So that's how. That's how. Now I again make a call to the left hand side, but then there is nothing. So I return. I make a call to the right hand side, there is nothing. I return, which means that this is a leaf node. Alright, all good till here. I return back to this point, and I make the rightwards call. Then what I do is, since this is 2x plus 1, I'll have the value of 2y plus 1 over here, where y is actually this whole value, 2x plus, right? I'll again make the left and right call, nothing happens, return, return. Then I'll make the rightwards call over here. I'll say that this needs to be 2x plus 2. Sorry, this is 2. Or 2x plus 2, so this would actually become this would have a value of 2. So that's basically, if I just code this particular logic up, I'm sure that's going to recover my tree, right? So yeah, let's maybe try to do that. Now the very first thing which I'll have to do is something like I'll have to update the root.val to 0, right? And then what I can do is maybe uh, make a recursive function, pass in the root and pass in the value of the root. Why I'm passing the value, maybe I don't need to pass the value, but then let's see, I'm not sure at this point. Let's see. So recur, you receive the root, you receive the value. All right, you can actually extract it by saying root.val as well, but then let's just pass it for now. Let's see what happens. Now what did we say? We said we are going to call towards the left hand side, right? The first thing which we are going to do is recursively call the function for the left hand side. So I'm going to do that. I'm going to implement that exact same thing. So for the left, what I'm going to do is call the recursive function, send it to root.left, and what, 2 into x plus 1. So 2 into value plus 1. I'm going to send this thing in the place of value. All right, sounds good till here. Thing is, I'm going to reach this node. Right now I'm standing over here. I have 2 into value plus 1, which means I have 1 over here. Then I'll have to assign it as well, right? I'll have to assign it to the current root.val. So root.val now becomes equals to whatever value is, and then it's actually good. So the first recursive, the first function call which I made was root comma 0. Now that means I don't even have to do this. It's automatically going to assign the value of 0 to my root over here. Then when it comes to the left, it's going to assign the value of 2 into value plus 1 to my left node, and again 2 into y plus 1, so on and so forth recursively. And then I just have to make the right recursive call. So what happens is basically, you know how recursion works. So I come to the left, I assign 2x plus 1, then I go back again, I make the recursive call again, I come to the left. The value over here was 2 into x plus 1, which means it was 1. Now when you make the recursive call over here, the value would be 2 into 1 plus 1, which is actually 3. And then if this node actually existed, it would have been 7, but this doesn't exist right now. So that's how the left recursive call is working. Now before we actually go on to the right, actually it's going to make the recursive call and it's going to find nothing over here. This is null. So what do you do then? You'll obviously have to have a base case. So if the base case would be if root is null, then just don't do anything, just return from there. All right, so when it explores the left hand side, it finds nothing, it just returns. Now it goes to the right hand side, finds nothing, returns. Then it's going to go towards the right, which we are going to code up at this point. Root dot right, it's going to be the same thing, but 2 into value plus 2 rather than 1, right? So it's going to go to the right, assign the value of 2 into 1 plus 2, which means 4, find nothing, return, and then do the same thing for the rest of the tree. I think this logic is enough. We'll see if we need to add something. and then what I'll do is for the find logic, so they're just asking me for numbers, right? If we talk about the brute force approach, then the very naive approach would be I traverse over the tree, and then if they want me to find one, I find one. If they want me to find three, I find three. If they want me to find five, I'll find five. But then obviously, as competitive programmers, as people who are obsessed with data structures and algorithms, efficiency and optimization, we can think about a better approach rather than traversing the whole tree each and every time again. What we can do is we can traverse it one time, either DFS or BFS, that's totally your choice. And then as you're traversing the tree, you store all the values in a set, right? Set of integers. Now, whenever they want you to find a value, you just look that value up in the set. So that's going to be computationally very better for you. But then if you're obviously in an exam, don't directly say we are going to store in a set. Start with the brute force approach. All right, say that we are going to find each and every value in the tree and then optimize that. Then tell them what's wrong with the approach what's wrong with the brute force approach, and then move towards something which is more efficient. All right. So yeah, what I'm probably going to do since we have already hit depth first search over here, we have talked about DFS over here. So let's maybe try to implement the find logic via BFS. All right. So after I have recovered the tree through recur, what I'll do is I'll perform a BFS function, and inside of I just want to store all the values in a set. So I'll pass in the root and I'll pass in my set. I have to create the set first. Let's keep, or maybe let's just pass the root, and for now let's just keep the set as something global. All right, unordered set integers st. All right, perfect. Now I'll have to create the BFS function. Void BFS only receives the node, the root. And what does it do? Let's see. So this is how my recovered tree looks like, right? I'm sorry. This is how my recovered tree looks like. If I paste it over here, oh, sorry. If I paste it over here, it looks something like this. So we know how basic breadth first search works, right? If we don't, let's see how it works. So I'll make a queue. And I'll just I'll just store this particular root, this whole root, not just the value, the whole root inside of this, inside of the queue. I'm just writing the value, but then remember that it's a tree node queue. Why it's a tree node queue? We'll we'll come to know in a second. Now, this is the first thing that I do. I push the 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 root inside of the queue, and then I explore further. So I'm going to take this, pop this, and store it in a variable, a temporary variable. Then I'm going to see if there are left and right children of this particular node. There are. So I'll push them into the queue. And now you know why it's a tree node is carried, because you obviously want to go towards the children of a certain node, right? If this was an integer queue and I was just storing integer numbers, then I wouldn't have been able to reach the children of this node. So yeah, I push 1 and 2. Then what I do is I remove this 1 from the queue. I see what its children are. I push them into the queue. Say, and you do so on and so forth. Not actually. I'll will I have to since will I have to remove these numbers from the queues? I would, because that's how we're going to explore, right? So yeah, as I'm exploring them, what I'm going to do is I'm going to remove them and then store them inside the set. Okay, so yeah, pretty basic logic. You are at this point, explore the children, then you explore the next thing, explore its children, come over here, explore the children, come over here, explore the children, come over here and explore the children. So that's basically how BFS works in very simple words. Let's implement that through code. All right, so I'm going to make a queue of tree node style, right? Of the nodes. I'm going to name it Q, and then I just need to push the root initially. Now there's going to be a condition. So yeah, till when I'm going to continue the process of searching till my root till my queue is empty, because when I explore 2, I remove it, then I explore 3, remove it, explore 4, remove it. At this point the queue is empty. I'm going to say, I'm obviously going to have a loop over here. I'm going to say uh, queue while queue is not empty, actually do something, and what that something is going to be is the exploration for which we are going to write the code. Yeah, so I'm going to say remove the current tree node, which is at q.front, which is initially it's going to be 0, and add it to the set. So set.insert whatever current is. All right, current dot value, actually not current dot value, because it's a unordered set of integers, and we are only, when the question asks us to find something, it just wants us to ask, it just wants us to find if that certain integer value is present or not. That's it. It doesn't, it doesn't require us to know the value of the address of where that node is present in the memory or anything like that. So we don't need to have an unordered set of tree node asterisks, right? Okay, so I insert the 0 in the set. Then what do? I explore left and right, just like we said over here. I'll see if there are children present on both of its sides. So I'll say if current dot left exists, then what you do is you put it inside the queue, queue dot push current dot left, and then the same thing goes for the right child as well, right? If the right child exists, then just put it inside the queue. And then if you dry run this logic on your own, what you will come to know is it explores all the nodes which are there in the tree, explores them. I also have to pop the values. So yeah, explores them, pops them, puts them into the queue, and therefore thereby you have all the values, all the recovered values inside of this data structure of yours, right? Now target implementing the find function becomes very easy. You're just going to say if the target value, whatever target value is, if it exists in the set. So st.find target, if it exists in the set, is not equals to st.end, you're going to return true, obviously, because it exists. Otherwise you're going to return false. As simple as that, right? So let's try to run this logic. Let's see if it works. Compile error root dot val root arrow val, right? I hope this works. I'm pretty confident. Current dot value, current dot value, it's going to be current this over here as well, current left, current right. Everything else looks good enough. Val value, not value, val. Yeah, very nice. Let's see if it passes all the other test cases as well, and then we'll have a discussion related to Zabardast. We have successfully done this question, and if we talk about the time complexity, then we can very clearly see when we were implementing the find elements logic, when we were talking about the recovery process, then we had a recursive function in order to recover the original tree. And what we observed in that case is that we just explored each node once. So that's something which is O of n, right? We're not talking, so as large as your input, only those many nodes are going to explore. And then we did the BFS traversal of the root in order to fill up the set. So that's again O of n, because you visit every node only once, right? And then the good thing is that the find function actually works in O of n. Why? Because you are actually looking up the values inside the unordered set. So this is going to be the time complexity O of 2, and basically reduces to O of n, and then this is going to be the space complexity. So yeah, pretty interesting question, a very good review of the DFS and BFS processes. And if you would like me to make more videos related to any problem solving topic, be it dynamic programming, be it combinatorics or mathematics, Do let me know in the comment, and I'll see you the next time. Take care till then.